Welcome to our second art tutorial for project 3. For this, we're going to use data sets that are already in R, so I do need to go ahead and load those, right? We can see my data set was loaded. Remember that if I put a question mark in front of a data set or in front of a function, it tells me a little bit about that function or that data set. Head of a data set gives you the first few lines of data. I always like to see what's going on. And str, that gives us the structure of our data set. So we know we're working with numbers and factors, right? So for qualitative data, get rid of that. For qualitative data, we need to create a table first. So I'm creating a table for the species of irises so I can create a bar plot for them. So I have 50 Setosa, 50 versicolor, and 50 virginica irises. Remember, this is a data set of irises, of 150 irises. So there's 50 of each. One thing I could do is I could give that table a name. I don't have to. But if I give that table a name, then I can just use that name to refer to it. So I'm going to run this line of code. I'm command entering, right? That's how I run it. So it gives me, okay, here's our table. I could also convert that table into proportions. I believe in nuclear reactor data set, that project 1, you needed to create a proportion, right? This creates a proportion. 50 out of 150 would be a third, or 0.333%. So what we want to make is a bar plot. And just as you can put a question mark in front of a data set, you can also put it in front of a function, and it'll tell you a little bit about that. So it creates a bar plot with vertical or horizontal bars. There's all these different options. We don't have to make it like this complicated, defining height and width and things like that. But what I want to do is I want to create a bar plot for my species. Now, if I just try and create a bar plot for iris species, that doesn't work because it needs to be organized in a table. So I'm going to have to create a bar plot of species table, or I could have put this code in there. I can show you that that'll make the same code. So let's run that. So we have our bar plot, 50 Setosa, 50 versicolor, 50 virginica. I could also make it of proportion. Species table. That runs it a little differently. Oh, proportions. There we go. You got to make sure you spell everything right. So now instead of giving you the frequency, it gives you the proportion. As always, I could add titles. Like I could add a title, proportion of flower, iris species. Let's see how that changes it. Okay, gives us a title. I spelled proportions right this time. I could also change the color and the cyan mood, right? So we can add these things. We could add X labels and Y labels. You guys know how to do that by now. But yeah, so this is our bar plot, right? I had to first put this qualitative data into a table. The second thing I want to talk about is box plots, right? Box plots. By box plot, this is what we mean by like a stem and leaf plot. That might be a good piece of information for us to have. Oh. So here I've got a box plot, right? We can even run an example sometimes. And so it gives us, well, this is a really weird looking one, but it gives us some box plots. So box plots, this is actually what we call box whisker plots, not stem plots, but box whisker plots, okay? So if I want to create a box plot, I first need to put in the sepal, what I want to create a box plot of, which in this case is going to be sepal length. I can give it a title, I can give it a Y label, I can give it a color. Let's change this color to yellow. So let's see what our graph looks like. Okay, so here's our graph. It is a yellow singular plot, and this is the sepal length of all of our irises. But what if I wanted to break it up by iris type? For that, I'd need to use some different code, okay? So here I have sepal length and this little tilde, which is my y. This little tilde, which is going to be our, tells us to divide it up by species to get the data from the iris data and give it a title, X label and Y label. Right here, we just had sepal length, that's our Y. Interestingly enough, the first thing you put in is your Y, followed by your X. So let's run this code. Okay, did that not work? Oh, I think I ended up in the wrong spot. So let me go ahead and run this code. And I don't know why I do this. You can have it on multiple lines, but I just never think to do that. So there we have our graph, and now you can see our X is divided up by iris species, and your Y is sepal length. And this is the same thing as above, so we don't need to run that again. Let's talk about mean, median, and standard deviation. So the command for mean is just the word mean, which is very nice. And it just wants you to, you put in what variable you are asking it to. You could also ask it to trim. You could also ask it to avoid whether NA values should be excluded, and that is crucial sometimes, right? The not available would help you calculate it. So if I type mean sepal length, it gives me the mean sepal length and the mean sepal width, right? The sepal is longer than it is wide. For median, you just use the code median. Again, let's put a question mark in front of that so we can learn a little bit about that. I definitely recommend pausing so you can run this code yourself, right? The best way to learn is by doing these tutorials. So, X, avoid all NA values. NA arm equals false. That means you aren't removing it. NA RM means equals true, means you are removing it, and you will need that for the brain data you'll see in project 4 and 5. So quick hint. So if I run that, it picks the median, middle length for sepal length, and sepal width. We can also calculate S standard deviation. SD is the function for standard deviation. You put in an X value, and again, you can remove NA values if that's necessary. Again, we don't have NA values in this data set. NA means not available, or there's a gap, right? We talk about cleaning data in data analysis, and that removes all unknown values. So we could calculate the standard deviation for the width, length, and then for the width. Okay. So now we know how to find some measures of center. Don't worry so much about mode. There's not really a good way to calculate mode in R, nor is it something that's typically asked for. So a big question is, how do we pick a graph, right? So let's say I wanted to plot sepal length, right? This doesn't work, right? What I've done is I've taken the index, so for flower number 1, here's its sepal length. For flower number 2, right? So we're taking the index from flowers 0 to 150, and we've just plotted them, right? This doesn't tell me much about how to pick a graph. Okay, so I can make a bar plot of sepal length. And well, this doesn't work because what it's doing is for each flower, all 150 of them, it's taking and plotting its sepal length. That doesn't really work. This doesn't tell me anything. One thing I could run is a histogram. As we can see, this graph looks a lot better, right? We can kind of see the distribution. It appears mostly normal, which is what we'd expect because, you know, irises or something that occur naturally. Another thing we can do is, this is by frequency. We could make it by percentage. We could convert that frequency to a percentage. And to do that, we would want to do this frequency equals false. That's kind of turning off the frequency. Convert to proportion, essentially. And now it calls it density. We could change the title if we wanted, but now it's converted to density. And once we do that, we need it to convert to proportion or density. We need to do that in order to add a line to our graph. What I want to do is I want to add a line that kind of represents the distribution, right? So let's go ahead and try it. Did this work? So this didn't really work, right? It gave me a straight line. One thing it says, if you look at lines, is you need an x, right? So I'm going to redefine our variable x as iris sepal length. So now you can see, okay, here's all these sepal lengths. Then I can create a histogram of x, right? But maybe for this case, I should give it a title. Because x, we know what x is. X is the sepal length. So this is a histogram of sepal length, right? We'll change the color too. Color purple. Is purple one of the coded in colors? Right? Okay, let's see if that works. So here we have our new graph. Oh, that's actually a pretty shade of purple. And then I can add my line. So my line is x, right? My line, what I want to do is put in x, where x is the density of x and the color red. This is the exact code that you're going to need for project 3, 4, 3. So let's see how that looks. Oh, look, we've got this beautiful line. It kind of fits. It's not perfect, but it's pretty darn close. Next, let's go ahead and talk about random variables. So I want to talk about generating random variables. And there's a couple ways we can do that. For one is by RUnif, right? Randomly generated numbers in uniform distribution. So this would be randomly generated numbers in uniform distribution. So you put in how many you want and your min and max. If you don't put in a min and a max, your default is from 0 to 1. So let's say I wanted to create 10 uniform variables distributed between 0 and 1. Here they are. If I want to, I can make those into a histogram, like so. Not super exciting, right? But I could make it bigger. I could do histogram of a randomly uniform distribution for, is this 100,000? No, it's 1,000,000. And look how this looks more like a uniform distribution than our original graph did. Notice how every time I run this, my graph changes. Where did my graph go? Here it is, but see, it keeps changing. So I can define a variable, right? Remember this little arrow? Arrow allows us to define a variable. So let me run that. So I've named x1. x1 has 1,000,000 entries. That's a lot, so it stopped typing them. I can also calculate the mean, median, mode, not mode, standard deviation, sorry. I can make a histogram. Beautiful, right? For our norm, what we want to do is we're going to generate random variables that fit a normal distribution. Before we did a uniform, now it's a normal distribution with mean of 0 and standard deviation of 1. These are our defaults. So it'd be our norm, however many you want, your mean and your standard deviation. So let's let x2 be our 100 randomly generated normal variables between normally distributed around a mean of 0 with a standard deviation of 1, right? I can calculate its mean, which would be really close to 0, right? That's something you'd expect if its default mean is 0. And then if I calculate the standard deviation, we would expect that to be really close to 1, right? Because our default standard deviation is 1. I can even make a histogram of this. I made it blue. So pretty, and look, it kind of fits that normal distribution. I can also change my mean and standard deviation. So here I'm creating 100 random variables that fit a normal distribution with a mean of 5 and a standard deviation of 3.2, because I can make it a decimal. You will then see that if I calculate the mean, oh yeah, it's pretty darn close to 5, and our median, well, oh yeah, that's pretty darn close to 3.2. Now it's not exact, but something we're going to cover later in the class is the central limit theorem, and you can see that if I made a big variable, right, then my mean gets so much closer and is practically 5, and my standard deviation is practically 3.2, right? Last but certainly not least, you can perform operations on your data. When our data sets are the same size, we can add them. So before we defined x2 as 100 normally distributed variables with a mean of 0 and standard deviation of 1, and x3 had a mean of 5 and a standard deviation of 3.2. So just showing you, we could add them. I could organize it as a table if I wanted to. We can subtract them. We can multiply them. We could multiplying them, that's the same as squaring them, right? We could even divide them. If I wanted to, I could define a new variable, x23, as x2 plus x3, right? I can graph the histogram, right? So here's our graph of our two normal distributions added together. I can subtract them, still normal. I can multiply them, skews to the left because our numbers get smaller. It looks the same as if I squared it, right? Like this is the same graph as if I had multiplied it by itself, and we can divide them as well, right? So here we have our beautiful R data that we've been playing with. Always remember to pick up your toys, right? You want to clean up your data.